Last time we looked at the binary search tree. It's a data structure that lets us add, remove, and traverse in reasonably fast time, and it lets us search very conveniently. However, what if it had a problem? What if we add to our binary search tree a data set that's already in order? That might sound like it's a blessing, like we're adding something that's already sorted. We've done the work, but look what happens to our tree. It just gets taller and taller and taller. And what do I mean by taller? Well, I mean that every node just has one child. So we have to traverse through all those nodes when we want to add. That is the key to the time complexity of our tree. Our methods are fast because they don't iterate over everything in our data set, but they iterate over the height of the tree where we're adding. Let's look at this search method for an example. Our search never goes up and then back to another child. It only goes down the chain of children, right? So the maximum amount of steps it can take is the maximum length of a chain of children it might have to follow. Same thing happens with add. So we can say that the time complexity of our tree methods is bounded by the number of children, the maximal number of children a node can have, which is what we'll call the height of our tree. So how do we make sure the height of our tree stays low? Well, let's think about a small tree, just of size 3, and let's try to apply those ideas recursively. In a tree of height 2, we have a child, a root, and another child. But we can also get this tree to be of height 3 if we have a root and then 2 children on one side. What does that tell us? Well, it tells us that a tree whose nodes are filled, a node which has both children, is going to be better for our time complexity than a node with a chain of children. And if we go through and we take this logic through a whole tree, we can say it's a complete binary tree where all of the nodes either have 2 children or no children. In this type of binary tree, we can actually observe a property about the way that our size relates to our height. When we fill a tree starting at size 1, it takes us 2 nodes to populate the children of that root. And then it takes us 4 nodes to populate the children of those children. And then 8, and then 16, and then 32, and then 64. And you know what that looks like? That looks like 2 to the power of n, where n is the height of the tree. So we can say that to get to height n, we need 2 to the n nodes in an optimal complete binary tree. So if we take the opposite operation of the 2 to the n power, and we apply that, then we get log base 2 of n as the number of height for the given number of node. So how do we get closer to this with our existing binary search tree? Well, let's take this unoptimized size 3 tree as our example. We've got 3 nodes in our tree, and they go root, left, left. What if we consider the properties of our binary search tree? If we go with lefty larger, we know that the root is going to be smaller than its left child, which is in turn going to be smaller than its left child. And we know that the root's right child must be smaller than the root. But we also know that the parent of the left child must be smaller than the left child. So since we know that both the right of the root must be smaller, and also that the parent of the root must be smaller, we can actually swap the positions. We can swap the role of parent with the role of right. We can reroute our tree. That's called a rotation. We take this tree of size 3, and we change the root from being what used to be the root, which is this edge, to being the center node with 2 children. And now our tree has gone from maximally unoptimized to maximally optimized. And this rotation can be applied, well, just like everything, recursively to larger trees. That's the first trick in our book of how to improve the binary tree. These rotations can be performed in a number of ways for a number of reasons. My favorite example is a tree which rotates itself based on how frequently you access certain nodes, which means it will actually get faster every time you access something, so commonly accessed items will be accessed in better time complexity. Good luck, thank you for watching, and I hope you enjoyed.